Time to get started. I know this is the same slide that I started with last time, but we're going to finish up talking about the solar system in general, and then on Friday, we'll talk about the Earth. Just right now, in case people took that and said, what? Why are we talking about the Earth? We're going to learn about the Earth because we have sent probes to visit Mars. And we famously have, Spirit and Opportunity up there roving around taking pictures. And I don't remember the names of all the probes. I think there is another one that's still running. So Curiosity is the latest one. Oh, the latest one. Okay. Anyway, the Russians have sent probes to Venus, which is really quite a feat because Venus has a very hostile atmosphere. I think 90 minutes is the longest anything was able to run before it was destroyed by the atmosphere and the high temperatures. And then we've sent explorers to explore all of the other planets. But we don't have the intimate knowledge of the other planets like we do of Earth. But we study what we can understand from Earth so we can look at other planets and use comparisons to try to understand them better. So I think we ended last class period with this slide on the densities of the planets and the compositions. And in fact, I know we did because I ended with it zoomed in like this. So I mentioned that each planet has a big rock in it. And you can see here's the size of Earth for comparison. Pluto has a small rock in it. Pluto's like half rock, half ice, we believe. How do we get half rock, half ice? How do we come up with that belief? Especially before last year when we had our first orbiter to visit Pluto for all of a day as it flew by. How would we determine that Pluto was about half rock, half ice? From the density. And how do we determine the density? Pluto is now known to have 5 moons. Hydra, Nix, I think Oberon. I don't know. I could be naming moons of Jupiter for all I know. I think there are Plutos, but the ones that we know, the one that everybody knows is Charon. And so with Charon and Pluto, they measure the orbit of Charon and Pluto. And because Charon is, a reasonable size compared to Pluto, you can't just take the form of Kepler's law that we learned initially. You have to use that the sum of the masses of the two is equal to the g, 4 pi, whatever stuff, and then the average separation cubed over the period squared. And so you get the total mass of the two by looking at their separation and the period of time it takes to orbit. Well, then you're like, okay, so I know the total mass of the two. How do I know how much each one is? To do that, all you have to do is locate the center of the orbit. We call it the barycenter, it has a name. But Pluto and Charon will be orbiting the barycenter, so you have essentially, here's Pluto. Come on, change colors. Here's Charon. And they're going around. Okay. That's the wrong way of doing it. Come on, undo. We're going to have Pluto, because it's more massive, is the one doing the smaller circle. And Charon, because it's more massive, is going to be doing the larger circle. They're always going to be opposite each other, and they're orbiting a specific point between the two. And then you just measure the distance from here to that point and there to the point, and the ratio of those two distances equals the ratio of the masses. So you can think of it kind of like a level problem. And so you get the total mass from getting the average separation and the period for orbit. And then you can separate which one has which mass by finding where the center of the orbit is. So just using Pluto and Charon, we can get an accurate mass for Pluto. And once you have that mass, then you just need to measure its size. Well, using a land-based telescope, we can resolve the size of Pluto. Kinda. You're not going to see these pictures much anymore, but the pictures we had of Pluto up until last a year and a couple months ago were fuzzy pictures. And so they kind of tried to guess what the actual diameter was. They said, okay, there must be some atmosphere here, and guessed at how thick the atmosphere was. And they used that to find the radius of Pluto and thus the density, the mass divided by volume. Well, when we had the orbiter go visit Pluto, they found that it had less atmosphere than they thought, which meant that it was bigger than they thought, which meant that its density was a little bit less than they thought. So the visit that we had 2 years ago helped us get a better number for the density of Pluto because it helped us to figure out its size accurately. So what we think we know, now think about Pluto, not that far away compared to a star. What we think we know is not always correct. And so astronomy, more than physics by a long shot, constantly updating, learning more, and having to update our hypotheses and theories as we get more information. So what are the densities like? The inner planets have densities somewhere in the ballpark of 5 grams per centimeter cubed. I shouldn't have put it like that. They range from about 3.3 grams per centimeter cubed up to about that. And the outer planet's density somewhere in the ballpark from 2 to 2/3 grams per centimeter cubed. And as Russell pointed out last class period, Saturn has a density that's less than 1 gram per centimeter cubed. Why is that curious? Because liquid water on Earth has a density of 1 gram per centimeter cubed. And so the density, the average density of Saturn is smaller than the density of water. And so it's a fairly low density. So as people like to say, Saturn would float in a bathtub. Yeah, not really if you start thinking about the sizes of things and the size of the bathtub, blah, blah. But it's an interesting comparison. That density, an object would float in a bathtub. So let's move on to our next slide. How did the solar system form? Who was there when the solar system formed? I thought you were going to answer, Tioni. Tioni's all me. I was there. No. God was there. I believe God was there. But no human was there to see the solar system form. Now, I'm a creationist, but my creation is, I believe that God created the universe by putting in the energy to form it and by putting the laws of physics. And then later on, he came and he acted on the earth to create life as described in Genesis. There are some creationists who have a different view here and say, well, the solar system formed because in the creation week, on the first day, God created the heavens and the earth. And so God created the solar system like it is now, pretty much, when he created the heavens and the earth. You know what I'm not here to do? I'm not here to indoctrinate you or to argue with you about who's right and who's wrong. So if you believe that, I am happy, right? I'm not going to say, oh, no, you can't believe that. That's not the scientific way. But I am here to make sure you do understand what the scientific answer is to that question so that you can compare and contrast. Here is what some people interpret the Bible to say. Obviously, you've heard my interpretation of the Bible just now. Here's what scientists who take as a starting point that if there is a God, he's not interacting with our world in any way. He's standing back and watching. That's how they come up with their interpretation. So I'm going to give you the scientific interpretation and understand its starting point is that if there is a God, he's not interacting with the universe. As a Christian, I obviously believe there is a God. I have to say this to be clear so people don't go home and say, would you believe my teacher said this? I've got it recorded. It'll be on YouTube. I believe there is a God. I believe he created all life, and he created the heavens and the earth, just not in the fashion some people do. But I'm teaching you the scientific interpretation without regard to what my personal belief is. Okay, we all understand the disclaimer. I'm not a heretic. We all agree with that? So, although you're not allowed to talk to your parents then. Okay, so here's the scientific model. They get this, scientific model. They get this information or these ideas from looking at the data they've collected, from looking at things like we talked about the general behavior of planets rotating in the same direction they're orbiting, from looking at the comets that you have the Kuiper belt that's in the same plane as all the planets are orbiting. So all planets in the Kuiper belt obviously are pretty much orbiting the same plane. But then further out, you have the Oort cloud that is going around in all kinds of crazy directions, but it's further out. From taking all of that information and taking the fact that the closer planets are different from the farther planets, scientists have come up with this to explain all of those observations. So they've gone through the scientific method, but it's a whole lot more intense than anything we did on the test. And so what they've come up with is a model that says, well, this is actually data they're trying to fit. I'm sorry, I thought that this was the model. This is the data they're trying to fit. So the rotation directions, the rotation planes, and the locations of the planets. This is just the information here. So we have what we call the solar nebula theory. Nebula is just the Latin word for cloud. So you could read this in English as the solar cloud theory. And the theory says that there was just a big cloud here. Big cloud of gas, fairly low temperature, so the molecules are going around kind of like slowly in a mosh pit, and they bounce off of one another, and not much is happening. And then something happens. When we learn about star formation, we'll learn more about this, but something happens to interrupt that system. Something whacks it. And when it whacks it, things get closer. What happens to the force of gravity when things get closer?
The force is greater.
Force is greater. And so when something whacks and they get closer, then the force pulling together gets stronger and it starts collapsing. Because of rotation, remember Aldrin up here, when Aldrin had the masses out, he was spinning around slowly. When he pulled them in, he spun faster. So as gravity pulls things in, it starts speeding up. And particles that are falling in hit other particles. And because they're hitting particles, they're exchanging energy. And they, because of all the collisions, they settle into a nice uniform rotation all in a single plane. And so that forming a single plane is a natural result of the collapse of a spinning cloud. And so that's the start for the solar nebula theory. You have this big cloud that was just, molecules moving around by random chance, a slight rotation preference. Collapsing that rotation really picks up speed and makes it flatten out. Yeah, question, Matt.
Yeah.
Max.
Do they have any theory on what the event was that caused it to start contracting?
Yes.
What do they say?
There are two things that can make it happen. They're both basically the same in the end. You have to have a shock wave hit it. A shock wave is just pressure wave going through space. And we tend to think that vacuum, it's vacuum between the stars, there's nothing there. Well, there might be 1 atom per kilometer, but that's not completely empty. And so this atom goes until it hits another one, that's how the shock wave goes through. And that shock wave could be caused by stars dying or by a few other things. And so what was the cause of the shock wave? There's no way to get a good conjecture on what it was for this specific instance.
So a shock wave could be just as small as an atom shooting through space until it hits another.
Well, not a single atom. It's a concerted atom. Examples of shock waves that you're familiar with. How many people have ever been boating? That wake is a shock wave. It's a wave that is a high enough intensity that it is traveling at the speed of a wave in the water, and behind it you have a different pressure situation that allows the water to go faster, and then the front edge is what stops it from going faster. That's what a shock wave is. I got a master's degree studying shock waves. And so you have a shock wave there, that's an example. Another one is a sonic boom. You have an airplane passing by that's going faster than the speed of sound. Then the airplane is outpacing the sound travels behind it, and it leaves a cone of sound going out. And when that sound gets you, you have sound from different times, emitted at different times, you hear all at once, so it sounds extra loud. So those are two examples of shock waves. And so a shock wave, something like that, going through space, it's not just a single molecule, it has to be a whole bunch of them. A tsunami is, I think tsunami is probably classified as a shock wave. You have still water in front, moving water behind. Have you guys ever watched video of a tsunami? growing up, I grew up in Monterey Bay Academy from the age of 5 to 17. And so as a young child, I was in fear of, tidal waves coming in. But I thought of tidal waves as big waves. A tsunami, the term tsunami is just Japanese for a harbor wave, which is a more accurate term because as a tidal wave, as this tsunami is going through a deep ocean, it might be, this tall. You can see it though. You can see it because in front of it, you have the water that's going like this. Behind you have all of the water moving together and compressed so that the ripples are much smaller. And so it looks like a shadow on the water behind the shock wave because of the difference in the water in front and behind. When it gets to shallow water, the energy has to go somewhere, so it builds up. And so the waves are only tall when you get to shallow water, hence the term harbor wave. But when a tidal wave hits, it's not like a normal wave because you have all of the momentum of the water behind pushing. So it's not just the wave breaks and that's it. You have more water just rushing up. And so it's relentless, whereas waves come in and go out. Okay, that was not our goal here. So getting back to this. After that shock wave causes the collapse, gravity is going to cause clumps to form. Where's the biggest clump going to form? Well, clearly at the center, because that's the position everything's being generally pulled toward. And so that's where the sun formed. But you have other clumps that formed outside that formed planetesimals, protoplanets, and things collided because you have lots of debris forming. And for each collision, there's one less thing that's out there to collide until we ended up with where we are today. So that's the scientific belief for how the solar system formed. It's called the solar nebula theory. Now we have the question of when, how long ago? And you see the time here, 4.6 billion years ago. 4.6 billion, it's a long time. Clearly no human is there to record this. So how do they get a number like that? I belong to a number of creationist Facebook groups, and the people there say, they pulled them out of a hat. Well, that's not true. They come up with the numbers for good reasons. So here's one, radioactive decay. Everybody's heard of radioactive decay. You may not realize that you yourself are radioactive. When I was in graduate school, one of my professors, the one who was the radiation safety officer for the college, said that if he were to take all of the radioactive material in my body and put it in a cube 1 centimeter aside, he couldn't give it to me because it'd be too radioactive to handle. Right? We all have radioactive things in us. Radioactive things are things that just the nucleus is not stable. You could view it kind of like I take these masses, and if I'm really tricky, I can maybe get it to stay there, right? But if I do something like kick the desk, it's going to fall over. And it's going to fall down so that they're both on the tabletop, and that's more stable. That's what's going on in the nucleus of a radioactive atom. The nucleus is in a configuration that's kind of stable, but if you kick it just right, it's going to fall down and go to a more stable configuration. And when it falls down to if that fell down, you would hear a sound come out, right? Well, in the nucleus, the energies involved in the nucleus are very large. And so when it falls down to a lower energy state, it's going to give off a lot of energy, either in the form of a photon, light, or it could be particles that come out of it. So that's what's going on with radioactive materials. The behavior of radioactive materials, when they decay, as far as we can tell, it's purely by chance. Quantum physics says that life is probabilistic, not deterministic. That is, we can only calculate probabilities because everything runs simply on probabilities, not on exact. You can't say this atom's going to go this long, this one's going to go this long. You can just say there's a 50% chance that in 1 hour this will decay. And so using those probabilities, we can say that if I start with, let's say it's carbon-14. You guys heard of carbon-14 dating? Okay, so carbon-14 is radioactive. It has a half-life of 5,730 years, plus or minus about 20 years. What that means is, in 5,730 years, half of all of your radioactive carbon-14s will have decayed back into nitrogen-14. So if I start with 1,000, okay, 1,000 is a pretty small number for statistics, but it's good for this. If I start with 1,000 atoms of carbon-14, if I wait 5,730 years, how many will have decayed? Half of that 1,000, so 500. So how many remain? 500. Well, if I wait another half-life, so another 5,730 years, right? There's no memory here, so I had 500. Wait another 5,730 years, half of those will have decayed. So I'll be down to 250 after 2 half-lives. And so with carbon-14 dating or any radiometric dating, they're saying, okay, we started with this amount. We now have this amount. What fraction is it? The amount that remains, what's labeled as fraction here, the fraction that remains should be 1/2 raised to the number of half-lives. So let's just, well, how old do traditional Christians believe the earth to be?
Like 6,000 years old.
Around 6,000 years. So if we use carbon-14, it has a half-life of 5,730 years. And so if the age is equal to 6,000, oh, let's be fun. Let's go 6,020 years. If the age is 6,020 years, how many half-lives have we gone through? Just over 1. And so I'm actually going to calculate n is equal to that age divided by the half-life is equal to 6,020 years over 5,730 years. And so putting that in a calculator, and I actually have one here that works even when the lights aren't on. I stole it from upstairs, don't tell anyone. That's 1.0506 half-lives. So what fraction should I expect to remain if the Earth is, 6,020 years? I should have 1/2 raised to the 1.0506. So that would be clear everything. 0.5, where's y to the x? Y to the x, 1.0506. So I should expect 48.3% of the carbon-14 that was present at creation to still be around. So that's basically the method that we use for carbon-14 dating or for any other radiometric dating. Now, carbon-14 has a half-life of 5,730 years. The amount of carbon-14 in things is a very small amount. And so for practical purposes, carbon-14 dating can only date out to about, at the most, 100,000 years. Most people actually say 50,000 years, some say 75,000 years. So carbon-14 is useless for ages more than 100,000 years. Now, if you are what we call the young Earth creationist, carbon-14 is absolutely relevant because 6,000 years is just over 1 half-life. That's about the perfect time to use to measure carbon-14 dating. But if you are an old Earth creationist or an evolutionist, you're talking about a little speck of time that's not useful at all in discussion of the age of the Earth. So you have different opinions on the utility of carbon-14 dating. But carbon-14 is not the only radioactive element. It's not the only thing used for dating. If you look back here at the periodic table, one of the most common dating things is potassium argon. They use potassium argon dating because potassium will decay and produce argon, or I said that backward. No, I said that right. Potassium will decay and produce argon. When the potassium decays and produces argon, argon is an ideal gas, a noble gas. Not ideal, it's noble. I mean, ideal gases are ideal, but not the other way around. So it's a noble gas. And if I have a molten rock, I might expect all of the argon gas to have escaped while it was melted. It's melted, it's high temperature. The gas molecules, like in water, you'll have the gas bubbles out, right? So when you have molten material, you expect most of that gas to bubble out. And then it freezes, you have solid rock, the potassium undergoes its decay and produces a gas, argon, that's now trapped in the solid rock. So it's a nice assumption to say that you started with no argon, and then you measure how much argon you have, and you measure how much of the radioactive potassium you have, you add the two together, and you get the total you started with, and you can do the calculation, find the fraction, and then find how many half-lives it's been. And so that's an initial presumption for the potassium-argon dating. Why is that good? Because the half-life for the potassium-argon decay is somewhere a few billion years. So it's just about right for dating things like the 4.6 billion here. But with radiometric dating, you have to understand it's not perfect. And a lot of young Earth creationists know it's not perfect, but they don't go deep enough to understand. So, does anybody see a flaw in the assumptions I've made when I talked about radiometric dating?
It assumes you have none to begin with.
Okay, with the potassium argon, we assumed we had no argon to begin with. Well, nobody's there to measure it. We know that we can have a hot rock and still keep some argon in there, and so that would cause an error. And if we talk about the carbon-14 dating, the mechanism for carbon-14 production is in the atmosphere we have nitrogen, right? The atmosphere is 79% nitrogen. And we have the cosmic rays from the sun will come and you'll have a particle from the cosmic rays hit the nitrogen, and the nitrogen produces carbon-14. I think it's a neutron, you absorb the neutron, it becomes, instead of nitrogen 14, it becomes nitrogen 15, which is unstable, decays into a carbon-14 plus a proton. Plus proton? Yeah, that should be right. So that's how it's produced in the atmosphere. That production depends on things like, well, if the sun is giving off more gases, you're going to have more production, right? The solar wind is stronger, you're going to have more production. If we have things like a volcanic eruption, we're going to change the gases in the atmosphere, and that's going to affect the carbon-14 in the atmosphere. So we know that carbon-14 doesn't remain constant. So what scientists have done with carbon-14 is they have calibrated by taking things that they can get an accurate date to. Things like, you have historical writings that say, at this time Hammurabi did this, and you find something that's referred to, and you say, okay, this had to be from that time, and then you do the carbon-14 measurement and say, it has this much, and extrapolate back to find out how much carbon-14 it started with. And so they do things like that, so they calibrated the carbon-14 historically so that they can then use it accurately. So nobody was back there to measure it, but they calibrated starting points. With potassium argon, it's a lot harder. Nobody wrote down what happened 3 billion years ago. But what they can do is look at different minerals and make measurements from each of the different minerals. And using some pretty complicated math, they can take the ratios of certain atoms from different minerals and determine what the starting condition was. So nobody in science uses an assumption of a known starting condition. You either have the calibrated starting condition from things that could be measured for carbon-14, or you have something like, the method is called isochrons, for doing the determination of how much argon you actually had when the rock froze. So there's good reason to trust the radiometric dating, in my opinion. Now, with that said, I have to point out another thing. I know I'm going way off base as far as astronomy. Wasn't me. Probably meant the Man City just won the game. It's probably what that was. So there's something to cast doubt in my mind about carbon-14 dating is the discovery of biological tissues in dinosaurs that are supposed to be 70 million years old. Now, 70 million years compared to 4.6 billion, that's still a small time, but biological tissue is not supposed to last in any situation. You put it in a deep freeze, the lowest we can go, you can't preserve it for more than like 70,000 years. So how could you have 70 million year old biological tissue? Which suggests that we have some gaps in our knowledge. Is our gap in our knowledge about the decay of biological tissue? Is it about radiometric dating? It could be either way. Could be both. But it's that radiometric dating that gives us the date for the solar system as having formed about 4.6 billion years ago. But that's not the only thing. That's one method of getting the age of the solar system. Here's a second method. The sun. We now understand the sun reasonably well, we think. It's fusing hydrogen to helium. We can calculate how much energy is produced by each fusion reaction. If we measure the light coming out from the sun, we can determine how much energy is produced per second. So we can determine how quickly it's converting hydrogen to helium. And taking its mass, we can calculate how much mass it started with. And finally, by comparing its size, mass, and temperature, we can make a determination of how old the sun is. Putting all of those together, we come up with the sun being about 5 billion years old and having a total lifetime of 10 billion years. So the sun's about halfway through its lifetime, and that age that we come up for the sun from those calculations matches the age that we get for the solar system through radiometric dating. So of course in science, when you have two completely separate methods of determining the age and they come to the same value, you're going to get a lot more confidence than you would if you had just one. If you had just radiometric dating, you wouldn't be as confident. But you have the sun as well, gives you more confidence. So that's why I personally believe that the solar system really is about 4.6 billion years old, and that the Bible story is true. It doesn't say when in the beginning was when God created the heavens and the earth. And so I say, well, the Bible doesn't say when. I'm going to go with the science here on the when. That's me. By the way, if you guys have things to interject, you guys know you can speak, right? Things that we have on Earth and in the sun. The sun is the vast, vast preponderance of mass in our solar system. So looking at the sun is basically looking at the types of elements that were available in the solar nebula. And so if you look at the sun, 70.6% of the mass of the sun, 91% of the total atoms, is hydrogen. And almost all the rest is helium. Just trace amounts of everything else. Clearly, if you look at Earth, that's not the ratios on Earth. The Earth is primarily iron, oxygen, and silicon. And so one has to ask, I mean, it should be obvious to anyone, the Earth is reasonably close to the sun. They formed, we believe, together from the same material. Why such different compositions? Of course, scientists ask that question. And so they want to answer, well, how did it happen? And you can see highlighted on this, the condensation temperature. Condensation temperature is the temperature at which molecules will stick together. So for instance, on a cold morning, I get in my car after going to the gym and my windshield fogs over. Why did it fog over? Because the windshield is colder when the molecules get to there. It cools them to the condensation temperature and they form water droplets on the windshield. The condensation temperature depends on the material. So you can see hydrogen, you have to get down to 180 kelvins for the hydrogen to condense and be in the liquid state there. Helium, you get it down to 3 kelvins, ultra, ultra cold. Well, near the sun, the temperatures weren't nearly that small. So you couldn't have near the sun hydrogen or helium condensing. But if you look at oxygen in silicates, silicates means things like quartz. Quartz is fused silica, for those who care. Silicates being silicon and oxygen compounds. It will condense at 1,300 kelvins. Now that's a toasty temperature. Likewise, iron, 1,400 kelvins. And so the theory is those are dominant elements on Earth because close to the sun, it was pretty darn hot where the Earth was forming. And these volatiles, the things that have the low condensation temperature we call volatiles, they couldn't condense. And so you couldn't have those clumping together to form a starting point this close to the sun. You would have to have a large object already formed before you could start holding on to them. And so the Earth being so close, it was hot here, and we could only really collect those elements. You go out further, the temperature is going to get colder as you get farther from the sun. And so you get to what we call the frost line. The frost line is the distance far enough from the sun where during the early stages of the solar system, it was cold enough that you could have these volatiles condense. Well, if you're past the frost line, that means you have these things that make the vast preponderance of the gases can clump together and stay together. And so all of this material that the Earth couldn't hold on to can clump together and be held onto out there beyond the frost line. So that means, the world's your oyster. You've got a huge collection of gas that you can hold on to out there. So they gobble it all up, and you get much bigger planets out there because it was cooler when they were forming. Alvin.
Before I forget, do we not have homework today?
That's correct. We do not have homework today.
Okay, thank you. I know other people had that question, and I was just like, I kept forgetting to ask.
Well, it's good that you asked. So now that you've memorized this table, select the 3 elements. So you're going to enter 3 elements and click enter.
Oh, can you just go back real quick? I just need to remember.
That comprise over 75% of the Earth's mass, but just over 1% of the sun's mass. And Max already knows who's going to answer this one.
It's channel 33, right?
Channel 33, that's correct. All right. What we have here is interesting. Now, I already know that Max answered this correctly. But Max, I want you to explain to everyone how, so I'm telling them which ones you chose, but explain to them how you made that connection.
I chose oxygen, right? Yeah, oxygen, silicon, and iron. That's what I thought I remembered from the table that was listed as the 3 big ones. But from what you were talking about, the reason why they believe that those are in the Earth but not so much in the sun is because of the high condensation temperature, and how when the Earth is forming close to the sun, the high heat could kind of clump them together and form the core or help form the Earth with those elements.
That is perfect. That's the reason, right? I know it's easy to forget which one's which, but understanding that concept of the why, that's what I wanted to hear. And so, yeah, you nailed the whole thing, so good. So I've already talked about everything on here. We can move from there. Once you have something clumped together, so you have condensation to clump something together, then you can have continued growth through further condensation or accretion. Accretion would be 2 clumps coming together and sticking together. So condensation is atom by atom growth. Accretion is clump by clump growth. And so once you form these, you get big enough and we say, hey, look, we have a planetesimal. We have a little growing baby planet. And so here is an artist's depiction, not a true photograph, in case anyone was wondering, of a disk with really nothing going on, everything going around the same direction because collisions have kind of made everything uniform. And then it starts clumping. And so you can see like here's a little clump and here's a little clump. You have clumps forming everywhere. And of course, those clumps, when they pass each other, there's going to be gravity and they'll be perturbed, start going in and out, and hit something. And when they hit something, they might stick to that thing and they might shatter it. But through that process, you're eventually going to get clearing of most of your debris as the bigger things develop more gravity and grab more things to them. And so that's one of the parts of what officially makes a planet is you have to have enough mass that when you go through, you clear your area of other objects. And so in this picture, it shows inner planets, a couple inner planets, the asteroid belt, outer planets, the Kuiper belt. And it shows collisions. Collisions is a big part of the history of our solar system, we believe. In fact, what would make the asteroid belt? I already told you the asteroid belt is actually a lot less mass if you combine it all together than one planet.
Isn't there a lot of space between?
Yes, that's right. The theory is that the asteroid belt was a growing planetesimal, became a protoplanet, started undergoing differentiation even, and then it had a collision with something that just shattered it. And all of those asteroids were probably part of the same growing protoplanet that got shattered. Another theory is that maybe it was just gravitational effects of Mars and Jupiter that did the work. So the stages of planet formation. First you have the planetesimals, the little tiny things. Then you get protoplanets, that's just a bigger version. And then when you get it big enough, gravity compresses and makes it hot enough that you start having melting. And when it's melted, well, then you have a liquid state. And as the picture shows there for the mint chip ice cream. Now this would be a sin, right? To take your mint chip ice cream and melt it. But you pretty much understand that the more dense materials are going to sink to the bottom and the less dense materials float up to the top, right? Just like if you throw a piece of wood and a rock into water, the piece of wood floats on top, the rock sinks to the bottom. So one of the first steps in planet formation, once you've reached a big enough chunk, is that it melts and differentiates. So the more dense materials sink to the center, the less dense materials float up to the top. Now, if you look at the Earth's crust is dominated by silicates. But we said we had silicates and iron, so where's the iron most likely? If it's not in the crust, it must be in the core. Why would the iron be in the core? Because it's more dense than the silicate, and so the iron sunk and the silicate floated up. To differentiate, separate. So the theory of what's going on in the center of the Earth is that we have a core that's primarily iron, maybe some nickel as well. So we have this iron-nickel core of dense materials that's swirling around, and then we have our silicate mantle and crust. So differentiation, the separation by density in the molten stage. I don't have this, at least on this slide, I don't think I have it coming up. After differentiation, you have a couple other things occurring. You have bombardment, lots of impacts, because in the early stages of the planets, you would have had lots of debris flying around. And so you have a reasonably large Earth, and you have a small chunk that comes and hits the Earth. Well, it's going to make a big impact, make a big crater, right? So it's actually that portion is called cratering, where you make the big craters because of the impacts of bombardment. But every time you have something that crushes into you and you hold on to, there's one less piece of debris out there to hit in the future. So the rate of impacts drops exponentially. So it should have been really high impact rates early on, very low impact rates now. Now, does the Earth still get impacted? Yes. I think it's once a month an object that is a couple meters across enters the Earth's atmosphere. They almost always burn up in the atmosphere. But it's kind of scary when you think about it. So we still have craters, we still have impacts in our atmosphere, but they're usually burning up in the atmosphere. After the cratering comes the flooding. Now, when I think of flooding, I think of water flooding the surface. But there are two kinds of flooding that we talk about in planet formation. There's water flooding the surface, and there's molten rock flooding the surface, magma flooding the surface. Well, what does that flooding do? It's going to smooth things out. You have a big crater and it floods, well, now you have a nice smooth region. And then the final stage of planet formation, so we had differentiation, cratering, flooding. The final stage is slow surface evolution. This is not some dirty word, evolution. It just means how it has changed over time. Slow surface evolution is the slow change in the surface caused by things like weathering and erosion. Weathering is breaking the surface. So like if you go to Holmes Lake and you just hike on down your own trail from the dam down to the water, you're responsible for weathering. You're breaking soil away. And then if it rains, the water will move that soil that you broke away, and that's what erosion is. So those things are going to cause a slow surface change. But you have to have the things that cause weathering and erosion. If you're on the earth, we have water on the surface. Lots of erosion and weathering things there. We have air. Lots of weather and erosion possibilities. But if you go to the moon, it doesn't have air or water. So the moon doesn't have any of that surface evolution, the slow surface evolution, because it doesn't have the things that cause weathering. So the moon's surface looks pretty pristine. You see lots of craters everywhere. Whereas on Earth, our craters have all been removed from the slow surface evolution. Now, one thing I have to mention, the moon has, in some places, like meters deep regolith. Basically, you had lots of little tiny impacts with sand-sized meteors that would have burned up in our atmosphere. And so it breaks it up and it's been like sandblasted. So you have this powder on the surface of the moon from essentially being sandblasted by small pieces of debris. It's very interesting. The atmosphere. I said our atmosphere is primarily nitrogen, 79% nitrogen, roughly 21% oxygen. Not the way it started, probably. Early on, we probably had an atmosphere that was mostly hydrogen followed by helium. Why? Because those were the dominant gases. But the Earth doesn't have a strong enough mass to hold on to them. Remember when we talked about escape velocity? The escape velocity for the surface of the Earth is 11.2 kilometers per second. Well, at everyday type temperatures, the speeds of hydrogen and helium atoms at that temperature is faster than the Earth's escape velocity. So they're going too fast, and we can't hold on to hydrogen and helium. Now, the Earth keeps producing helium through radioactive decays, but hydrogen, fairly limited. Now, we have lots of water, thankfully, that holds on to hydrogen. So our first atmosphere would have been lost. Second atmosphere should have been what forms from outgassing. You have hot rocks, lava, that will release lots of gases like methane and ammonia. Those are not good gases for us. Unfortunately, those gases have also disappeared, and we now have what's believed to be a tertiary atmosphere, possibly brought to us by comets. Some people believe that all the water on Earth came from comets that hit the Earth and brought the water to us. So our atmosphere today is believed to be a third atmosphere for Earth. Yes, already talked about the things there. Let's go to another question. How can this theory be tested? Now, this is one where you can answer multiple answers. So obviously, if you believe it's A, you just put in A and enter. If you don't believe it's A, then you choose from the smorgasbord B, C, and D and hit enter. Thank you, Hannah, for showing me that it works. And for that matter, Tioni, Max, Gabby, Connor. Latifah, Jessica, Daniel, Dari, Amelia. There we go. Everybody's answered. I care mostly, Aldwin, that you're trying.
I just didn't mean to send it like that. My watch beeped and then I pressed that.
Okay, starting over for the second time answering. Woohoo!
And it's out.
Aldo thinks it's him. Let's see. It is Yari.
So I kind of made a mistake in type 2, but I meant to just put C. And so I just pretty much guessed, but from what I remember, like you were talking about probabilities, so that's why I thought it would be that one, because like maybe we can have an idea of this by doing that observation, comparing it. But
Okay. I'm happy with your answer.
yeah.
I consider both C and D to be correct. Because now, if we can't test it, it's not scientific. Hence, we're not going to be talking about it in astronomy class. B, it can be tested by creating a new solar nebula. Good luck with that. 2 people said we can, though. C, it can be tested by determining predictions of the theory and then comparing to observation. That's exactly what the scientific method is, right? We look at our theory and we say, what does it predict should happen? And then we look for that thing, the outcome that, something else we haven't observed yet that should have happened. We say, well, that should happen too. And we look to see signs of it. The last one is a big one that's used in astronomy, computer modeling. Take everything we understand about physics and put it in the computer and say, okay, here's our starting system, big gas cloud. Here's the shock wave that hits it. Now what happens? And so that's a big thing used in astronomy is that modeling. And yeah, we're out of time.